All right, let's get started. So I want to finish up a little bit of the discussion on set cover, but a slight variation of set cover, which is also very useful in various applications and so on. It's similar to set cover in the sense that you have a universe of n elements and you're given m sets, which are subsets of the universe. In the set cover problem, you want to find the smallest number of these sets which together cover all the elements, right? But here, you're given a bound on how many sets you can take. So you're given k and you say you can't take more than k, and you want to cover as many as you can. Okay? So you're allowed to, I give you a number k and I say you can't take more than k sets, but you have to cover as many as you can. Right? You can see that it's kind of closely related to set cover, right? Because if you can solve this, you can solve set cover, right? Well, the other direction is not so obvious, but they're kind of closely related. And even for this problem, the greedy algorithm is very natural, right? You know, you say you pick the largest set, first iteration, and then you pick and you remove all the elements that are covered, and then you find the next largest set. When you think of how many, when you count the number of uncovered elements, you again pick the next largest set, and then you do that again till you get k sets, and then you stop, right? So the greedy algorithm, in set cover, you keep doing the algorithm till you finish covering all the elements, right? Because you're trying to cover everything and minimize the number of sets. Here you have to stop at k, right? You can't take more than k sets. So you keep on taking the greedy set as long as you don't exceed k, and as soon as you exceed, as soon as you reach k, you stop. Okay? Makes sense? The algorithm makes sense? Yeah? Okay? So now, remember, you know, this is a maximization problem, right? It's not minimization, because our objective is to maximize the number of elements covered, not minimize the number of sets, because we are given a bound on the number of sets already. So you're supposed to pick k sets, right? So the question is, how well are we going to do in this algorithm? Okay? And so the analysis is very similar to the algorithm, the greedy analysis for set cover. I'm not going to do the analysis because it is very similar and it's useful for you to read it, but I just want to state you will see that the analysis looks exactly like the same thing. What you can show is that at the end of the algorithm, the number of elements that you have not covered from optimum, that is, you know, in fact, optimum minus what you covered is less than opt times 1 minus 1 over k to the k is less than opt over e. Okay? So in effect, what you can prove is that you will cover at least 1 minus 1 over e times opt. Okay? So what is 1 minus 1 over e? It is about 0.632. Okay? So what this says is that you will cover 0.632 fraction of what the optimum would cover. Okay? So we kind of saw this earlier in set cover too, right? You know, what happens is that after you pick k star sets, you will cover 1 minus 1 over e fraction of all the elements. Here we are not thinking of covering all the elements, we are comparing ourselves to what optimum can cover with k sets, which may not be everything. Okay? Okay? So for this problem, you are getting a constant factor approximation, right? You know, that you're getting at least, I'm not exceeding the number of sets, but I'm covering a good constant fraction of the elements that the optimum would cover with the same number of sets. Okay? You can derive set cover analysis by just knowing this. Okay? If you want, that's another way of thinking about it. And so you can show that greedy gives a 1 minus 1 over e approximation for max k coverage. Okay? And again, this problem is very fundamental because of two reasons. One is that, again, set systems are very abstract, right? You can think of modeling many things as set systems. So this is a very generically applicable theorem, right? And greedy algorithm is very natural. And not only that, you know, the proof is not using very much about set systems really. If you think a little bit more abstractly, in fact, one realizes that the proof uses only what is called submodularity of the objective function. This is kind of, I don't want to go into technical details, but it's a very natural property of diminishing returns, and so this class of functions called submodular functions, and this is a simple example of that. So one can show that this 1 minus 1 over e approximation applies not only for this class of functions, but a much larger class of functions. Okay, and because of that, the number of applications is also very large, because the more abstract the theorem is, or the more general the theorem is, the more applications, right, and the more common the phenomenon is. And why only k sets? You know, you see, this is a very simple constraint, right, that I can't pick more than 100 sets. That's one type of constraint. But maybe, you know, you want to think about more interesting applications or problems. Or look, you know, my sets are colored into red, blue, and green, and you can't take more than 100 red sets, 50 green sets, and 30 blue sets. Right? That's a natural constraint you may have, right? And one can show that, you know, even under this kind of more complicated constraints, and even with submodularity, you can get good algorithms, heuristic algorithms. Okay? So because of all these reasons, there are many applications. And surprisingly, and a very, you know, very non-trivial result, one can show that you cannot beat 1 minus 1 over e in the worst case unless p equal to np. Okay? So this simple greedy algorithm is already tight in the worst case unless p equal to np. You can't get better than 1 minus 1 over e. Okay? Which is not easy to prove. This is a highly mathematically sophisticated theorem. Okay? How do you prove such things is beyond the scope of this class. Okay? But so that's also pretty, that you can get such a nice, this beautiful number, right? You know, it comes from a simple analysis, is actually tight. Okay, so that's all I wanted to say about set cover and max coverage. I'm going to now talk about TSP for a little bit, and then we'll see what we can say about TSP. Okay. So today's lecture is mostly okay. 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 So you recognize some of these towns, I hope, right? You know. Springfield, Urbana, Danville, you know, not the Paris you think about, but Paris, Illinois. So in Lincoln's time, Lincoln was a lawyer, as you may know, right, in Illinois, right? How many of you knew that? I guess most of you, right? You know. So in those days, the courts went to the people rather than the people going to the courts, because it was hard for people to go to the courts, right? So Lincoln used to go, he was a circuit court lawyer, and so he would travel around the counties, right, to set up court and argue cases and stuff, right? So this is how he would go, right? This is his tour, right? These are all the towns he had to visit, cities he had to visit, right? So his goal was to, I mean, one of his goals was to minimize the time he took to finish this tour, right? So that's really the traveling salesman problem, right? What is the traveling salesman problem? That you're given a bunch of cities in some metric space, or in general, you're given some distances between cities, and you want to start somewhere and visit everybody and come back to the starting point, okay? And you want to minimize the amount of time you go traveling. Okay? Is that clear, what the traveling salesman problem is? Yeah? Okay? And it's a very natural, simple problem, right? You know, you can imagine that there are various applications other than Lincoln traveling, right? You know, you know, it's not obvious. In fact, this is not really the optimum if you look at it as a points in the plane. But then you also have to worry about roads actually being there, right? You know, you can't say I can jump from, you know, here to here if there is no road from there, right? So So it's not obvious what they, and there are also obviously many other side constraints, right? You know, you have to travel during the day, or right, you know, you can't just travel whenever you want, right? Okay, but that's the most basic problem, right? So mathematically, how do you want to think about traveling salesman problem, right? So the very formal definition goes like this, right? You're given a graph. For now, we'll assume it's an undirected graph. We'll also later on consider directed graphs. So I give an undirected graph, and each edge has a cost. Okay? And what do we want? We want a tour, right? Or we want to visit every city, right? And come back to the starting point. So what is that? In a way, it's a Hamiltonian cycle, right? So what you really want is to find a Hamiltonian cycle of minimum total edge cost. Yeah? Okay, that is the problem. Okay? A graph can be undirected or directed, but first we'll think of undirected graphs. But the directed graph is more complicated, we'll see. And you know, for various reasons, it's not all applications. For historical reasons, the traveling salesman problem is very important in discrete optimization, right? It's because somehow it became central for many reasons, right? And so because of that, a lot of energy is spent by people on traveling salesman problem. And consequently, many ideas came out of trying to solve traveling salesman problem in theory and practice. Right? So it's a large literature on this problem. Okay. So we'll do so if you think a little bit about that, you know, we can sort of say, okay, look, you know, for simplicity, let's take the graph and make it a complete graph. Okay, what does it mean, make a complete graph? You add all the edges, but when you add a new edge which is not in the original graph, make its cost infinity. Okay, that's okay, right? Because if you make it infinity, you don't want to take it, right? One thing it does, it will help us a little bit when you think of other things, is that once the graph is complete, at least we now know that there's always going to be a Hamiltonian cycle, right? In general, we may not know whether there's a Hamiltonian cycle, but now we have a Hamiltonian cycle. Because it's a complete graph, there's a huge number of Hamiltonian cycles, right? Except that, you know, if you take a Hamiltonian cycle in this new graph, which is complete graph, if it was not a Hamiltonian cycle in the original graph, its cost will have infinite cost edges, right? So still we are preserving everything properly, okay? So that's one way of thinking about it. Okay, some special cases which are obviously important, we'll come back to this. One special case is what's called metric TSP. So think of the Lincoln store or something like that, right? You know, where are there points on the plane or where, you know, the distances satisfy triangle inequality. Okay, it's called metric. That is, you know, the vertices or points are in a metric space like the Euclidean plane, where there's a complete graph naturally, and there's a distance between every point. And what property does the metric satisfy? That, you know, the distance between u and v is the same, right? It's symmetric, right? U to v is the same as v to u, right? So it's an undirected graph. And moreover, you know, if you want to go from u to w and you go through v, it's cheaper to go, or no more expensive to go from u to v w directly. Yeah, that's called the metric property. So that's an important special case, right? There may be instances where that's not true, right? But this is an important special case that's called metric TSP. The even more special case is the points are really in the plane or in 3 dimensions or 4 dimensions or whatever number of dimensions, and the metric is induced by Euclidean distance or L1 distance or whatever distance you want, some norm distance, right? That's called geometric TSP. Okay, geometric TSP is a special case of metric TSP. Right? Okay. So another interpretation of metric TSP, which is actually more important to understand, is the following. Take, for example, the original problem, right? Or say the Lincoln store or something like that, right? You know, so why do we want a Hamiltonian cycle? We really don't want a Hamiltonian cycle necessarily, right? What is it that we really want in many applications? You want to start at a point and you want to visit everybody and come back to the starting point, right? I don't care if you visit a point more than once, right? You may have to go back to some city because there is no other way to go or something, right? So that's okay, right? In some applications, maybe it's not okay in some other applications, right? So I want to claim that that's another what does it mean to say that I want to find the smallest tour which visits everybody, but I don't care whether you visit a vertex more than once, right? Otherwise I come back to it many times because that's the only way to travel everything. Okay, I want to claim that if you want to solve that problem, that's the same as saying my graph is a complete graph and the distances satisfy triangle inequality. Why? If I gave you your original graph, you take what is called the metric completion of that graph. What does it mean? You compute shortest path distances between every pair of vertices, okay, and put that distances on the complete graph, okay. Then my claim is finding a Hamiltonian cycle in that metric completion is the same as allowing the tour to visit a vertex multiple times, okay. So we'll come back to this point again, but I want to make it first in a sort of a high level and we'll come back to that, okay. Okay. So in general, let's look at TSP. Can we, we know TSP is NP hard. Why is TSP NP hard? In fact, it's impossible to even approximate it. Okay, why is that? Formally, let's look at it this way, right? So if I give you a graph, we can't even decide in polynomial time unless p equal to np if it even has a Hamiltonian cycle, right? Yeah? We can't tell whether a graph has a Hamiltonian cycle unless p equal to np efficiently. Maybe if p is equal to np, then clearly we can do it, right? But we don't know. So in the case of TSP, the full generality, we can't even find a solution. Forget finding a good low-cost solution. Does that make sense? Yeah. So in fact, in this case, the problem cannot be approximated really. How can you approximate some good cost if you can't even find one solution efficiently, right? Does it make sense? Yeah. Okay. So in a way, the most general TSP where you really insist on finding a Hamiltonian cycle is what is called inapproximable. In other words, it says, you can't even find a solution. Forget about finding a good solution. Okay. So that was not true of other problems, right? If you want to find an independent set, you can take one vertex, it's a feasible solution always, right? If you want to find a vertex cover, take all the vertices, it's a feasible solution, right? It's not difficult to find one solution, it's difficult to find a good solution. In the Hamiltonian cycle problem, I can't even check whether there's a Hamiltonian cycle, so it's actually finding a minimum cost Hamiltonian cycle is, you can't even find one Hamiltonian cycle, right? So that's not a good, in that sense, it is inapproximable. So for that reason, we'll focus our attention on the metric TSP. Okay, what is metric TSP? It's a complete graph, right? And distances satisfy triangle inequality, so there is always a Hamiltonian cycle which is of some cost, and not only that, we'll see that it's actually an easier problem, okay? Because finding a tour is easy, right? You can always find a tour visiting everybody. How will you find always a tour that visits everybody? And we'll see that is actually very simple, and that you will find a simple algorithm. In fact, you can show that metric TSP is also NP hard, okay? Using Hamiltonian cycle. I'll leave the proof. The proof is there. Okay. So this is a very simple approximation algorithm for metric TSP. So the right way of thinking about metric TSP is that, one way of thinking about metric TSP is that I just want to find a tour that starts at some vertex and visits everybody and comes back to it. I don't care if you visit a vertex more than once. Okay? I don't really care for a Hamiltonian cycle. I just want to visit everybody at a low cost. So here is a very simple algorithm that is well known and folklore, right? Okay, what you do is you compute a minimum spanning tree in the graph. Okay, I give you a graph G, right? Okay, you compute a minimum spanning tree. Okay, and then you double all the edges. What does it mean, double all the edges? You make it 2 copies of each edge. So now you have what is called a multi-graph, right? Yeah? Okay. Now I want to say that, using this multi-graph, I can visit everybody, right? Okay, how will I do it? Here is, you can do depth first search or something like that, right? Okay? Okay, so how will I do it, right? Maybe I start here, right? I go like this, I go like this, you know, I go like this, I go like this, like this, like this. I mean, there are many ways of doing it, but, right? This is called Eulerian graph, right? Yeah? Another way of thinking is, you know, if you have a rooted tree, if you do a depth first search of that, you will go down, you can come back up, right? I will use an edge only twice, right? Okay? Okay. So is this a tour of everybody? Yeah? It's easy to see, right? What is the total distance I traveled in this way? Right, you know, the total amount of distance I traveled is 2 times the total length of the tree, right? Yeah, because every edge I traverse in 2 directions. Yeah, okay. So my claim is that, you know, I'm visiting a vertex multiple times, right? I'm okay. So, but well, you know, how much is this compared to the optimum way of traversing everybody? Well, I want to claim that the cost of the minimum spanning tree is no more than the optimum solution cost, right? Why is that? Sorry? Yeah, the solution is already, at least, I mean, it's connecting everybody, right? The solution visits everybody. If you think of it as a cycle, it's also a tree, right? You know, it's more than a tree. It has one edge more than a tree. So it's a valid tree in the graph, complete graph, and obviously the minimum spanning tree has to have a cost less than any tree, right? Okay, so the optimum solution has to pay at least the minimum spanning tree, yeah, and I'm paying 2 times that, yeah. So my solution is at most 2 times the optimum solution cost. Agreed? Very simple, right? You know, almost trivial, right? Yeah. Okay, good. So metric TSP is easy in that sense. You know, this is all I said, and okay. Everybody makes sense? Okay, this is good. Okay. Now the thing is, you know, can we improve this? Can we improve this simple heuristic? That seems so silly. Maybe we should be able to improve it, right? Okay. And obviously people thought about it because TSP is very important, right? So to make sure that we are on the same page, not all of you might have played around with this notion of Eulerian graphs. So how many of you have heard of Euler tours? Or who has not heard of Euler tours? Just, you know, it's okay, don't be shy. Or you have not heard of Euler. Okay, good. So what is an Euler tour? An Euler tour of a multi-graph, I have edges more than once, is a tour that starts at some vertex, comes back to it, visits every edge exactly once. So it's a walk which visits every edge exactly once. Okay. So for example, if I have a graph like this, then clearly there is an Euler tour of this, right? You know, I can go, the cycle is okay. Let's take it more complicated. You know, when I was a kid, I think I was below 10 or something. For some reason, you know, this I still remember from all these years, right? So they would give me this, I mean, I don't know why it was like, I don't understand the origins now, right? So this was the graph, and they said, you know, more or less they asked, does it have an Euler tour? Okay. And I didn't know any math, right? I was 8 or something, 9. So it doesn't have an Euler tour. You can enumerate all possible ways of doing this. It doesn't have an Euler tour, okay? And why is that the question, right? Okay, and why do you think it is? Okay. Okay. Why can't it have an Euler tour? Remember, what is an Euler tour? Yeah.
Because each of the vertices have 5 edges coming out of it, so if you leave and try to come back.
Right, right. You know, if the degree of any vertex is odd, I have to enter the vertex once on an edge, right, and leave that vertex on an edge. I can't use an edge more than once, right? Exactly once I have to use. But if the degree is odd, how can I do it, right? Because each time I visit a vertex, I'll use up 2 edges exactly, right? So I can't have an Euler tour if any vertex has odd degree. Yeah? Okay, but it's not obvious completely that if I have a vertex with odd degree, there is no Euler tour in that graph. Yeah? Is that clear? Okay. But the converse is also true. Every vertex has even degree, then there is an Euler tour in that graph. Okay? If it is connected, if the graph is not connected, if there are two pieces, then clearly I can't go from this to this, right? If the graph is connected and every degree is even, there is an Euler tour. Okay, what is the proof of that? Okay, yeah, what you can do is you can start at a vertex and go around, right? And what happened? You go to a vertex, pick an arbitrary edge, go to somebody, right? Or clearly the graph cannot be a tree, right? If the graph is a tree, there is a vertex which is a leaf which has even odd degree, right? So there is some cycle in the graph, right? Yeah? Remove the cycle. What happens if you remove the cycle? Every degree is still even, right? Okay? And now you can apply induction and combine it with the cycle. Okay? Because now it may be disconnected, but the cycle must have connected it, and so you can patch things together. There are many simple proofs, not very hard to prove. Okay? Okay? So this is what Euler, why are they called Eulerian? Because Euler proved this in whatever, when is it? 1600s or something, right? The Euler, the Königsberg bridge problem, he solved it using the notion of graph theory. Okay? And so that's why it's named after Euler, right? So an undirected multigraph is Eulerian if and only if G is connected and every vertex degree is even. Okay? And there is also a similar notion in directed graphs. The notion of directed graphs, the right notion turns out that the in degree must be equal to the out degree. Okay? A graph is called Eulerian in a directed sense if the in degree is equal to the out degree, right? Otherwise, if I come in once, I have to be able to go out, right? So that's called Eulerian graph, okay? In directed graphs. Okay, that's the background. Okay, so now let's go back to the TSP problem and say, can we improve the algorithm a little bit? Okay, can we get a better bound, right? So what did we do, right? We computed the spanning tree and we wanted a tour, right? But what is a tour, right? A tour is really like a cycle, right? If we want a tour is like a cycle. Another way of thinking about it, finding a tour is I want to compute the minimum cost Eulerian subgraph of the original graph. Why is that? Because a tour is clearly an Eulerian subgraph because it's a cycle. If I had an Eulerian subgraph of the original graph, I can actually visit everybody, right? So they're equivalent in some sense as far as metric TSP is concerned. Okay? Finding the optimum tour is the same as finding the minimum cost Eulerian subgraph of the original graph. Okay? Okay, so how do we find it? And here is Christophidis' idea, right? He said, what did we do in the spanning tree heuristic? He said, we took tree T, which we know is no more than optimum, and then we doubled every edge to make it Eulerian, right? It makes, if you double every edge, every degree becomes even, right? And so that's why we could traverse everything. So is there a better way of converting the tree into an Eulerian graph without doubling every edge? Okay, can we make the tree Eulerian without doubling every edge, and will it buy us anything? Okay, and so that's what he's thinking. He says, compute again the same thing, compute the spanning tree, minimum spanning tree in G so that we connect everything. But let's make it Eulerian without doubling every edge. Can we do it right? Is the question. Okay, so he said, okay, how can I make this tree Eulerian? Why is the tree not Eulerian? Well, because there are many vertices in the tree which have odd degree, right? Including the leaves, of course, right? Okay. Okay, so he said, let's do the following trick. Okay. Look at all the odd degree vertices. Look at this spanning tree. What are all the odd degree vertices in this spanning tree? Well, clearly all the leaves have to be odd degree, right? Even this vertex is odd degree, right? Okay. So there are in any graph the number of odd degree vertices is even, right? Okay. Is that clear? That's a simple observation. In any graph, the number of odd degree vertices has to be even number, right? Okay. So there are how many here? 6, right? And he said, I want to make these odd degree vertices even. How can I do it? Well, let's find a matching on them. Let's pair them up. Okay. So I want to add extra edges. So like this maybe, so that I pair up the odd degree vertices and add extra edges, right? So if I add one edge incident on an odd degree vertex and an edge connecting two odd degree vertices, then clearly both of them will become even, right? Okay. So if you can find a matching on the odd degree vertices of the spanning tree and add those edges, then I'll get an Eulerian graph. Yeah. And then I can find a tour of that Eulerian graph which will visit everybody, right? What is my cost? My cost is the cost of the spanning tree plus the cost of these matching edges, right? Yeah? Yeah, do you see that, this, what I've done is I've added some edges, we are matching on these odd degree vertices, and then I can make, this is an Eulerian graph, and this is a 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, right? And what does this shortcut mean? That remember our graph is a complete metric, is a metric, right? So if I'm going from, instead of doing 6 to 4 and 4 to 7, I can actually go from 6 to, that's the number of the edge. Instead of going from this vertex to this and then coming back, I can go directly there, right? That will only make it cheaper because I assume that the graph is a complete graph with satisfies metric, right? It's the same, it's equivalent, okay? Okay, so this is called the shortcutting of that tour. Okay, okay, is the algorithm clear? Okay, so what matching should we find? We should find the minimum cost matching on the set of odd degree vertices, right? If you want to reduce our cost, we want to find the minimum cost matching. Yeah? So we found the MST, then looked at the odd degree vertices, and then found the minimum cost matching on that. Okay. Now the only question is this any good? Right? Is it any better than the MST heuristic? Okay. And it turns out that it is better, and you will get actually 3/2 approximation if you did it that way. Okay. And let's try to prove that. Okay. How does it work? I want to prove that the cost of the minimum cost matching on S is no more than optimum over 2. Okay. Is this clear? I mean, this is the lemma I have to prove. If I prove it, then it's obvious, right? Why? Because my cost is the cost of the spanning tree plus the cost of the matching, right? And we already argued that the cost of the spanning tree is at most optimum. I am claiming that the cost of the matching is no more than half of optimum. So if you put them together, I get that the cost of my graph is no more than 3/2. Yeah, and that's all I pay, right? I don't pay anything more than that. Okay? Okay, why is this the case that the cost of the matching is small? Okay? Okay, for that let's look at a very simple lemma which says the following. I'm in a metric space, right? Say I have points in the plane and I want to visit everybody. I have a cost for the TSP, right? Okay, but now I say I don't want all of those points. I want only a subset of these points. I want a TSP for a smaller set. Will the cost of the TSP go up or go down? Okay, I mean just think of points in the plane. See, I have these points, right, initially. And I want to find a TSP of these points, right? Okay, but then I say, no, I don't really care about all the points. I only want a TSP on these 6 points. Will the cost go up or go down? Sorry? It can't go up, right? Why? Well, this is where we are using the metric property, right? Why is that? Well, let's see. Why is that the case? Right? Maybe my TSP tour of the original thing was like this, right? I am not sure what I'm doing here, but okay, all right. Maybe that was my TSP originally, right? And then I say, okay, now I can create the following TSP, right, a tour, which is not going to have any more cost. Here is my new TSP. Okay, I go in the same order. Okay, yeah. Okay, my claim is the pink tour is no more expensive than the red tour. Why is that? This is geometry, I mean, right? Why is that? Well, going from here to here, I could have gone like this too, right? Yeah? But this pink edge has to be lower cost than this way of going, right? Yeah? So same thing, this we are okay, this we are okay, but look from here to here, how can it be more expensive than going here, right? Yeah, because we are in a metric space, right? So we can go, it's only going to be cheaper to do the pink thing than doing the red thing, right? So if I take a subset of the points, the tour cost can only go down, okay? Okay, so now let's prove the lemma, right? Okay, again using the same picture maybe, right? Okay, remember, okay, we computed a spanning tree on the graph, right? Originally, and what was the set of, we looked at the odd degree vertices, right? Okay, okay, so think of these circled points as the odd degree vertices of the spanning tree. Okay, I want to prove to you that there is a matching on them of cost no more than opt over 2, right? Okay, how am I going to prove it? Look, we know that there is a cycle on this pink cycle on these odd degree vertices whose cost is no more than optimum, right? Why? Because we can take the optimum entire cycle and make it smaller, visiting only the odd degree vertices, and that cost is no more than opt. Okay? Okay, but I want a matching, I don't want a tour, right? I want a matching. Okay? How can I argue that there is a matching of half the cost of this pink cycle? I can take, here is one matching, right? Here, let's take two. Okay, so I have a let's give it. Okay, so here is one matching. I take this edge, and what is the other edge? This edge. Is that a matching on the vertices? Yeah? What is the other matching? I flip, right? Okay, because the number of vertices is what? Even, right? I can do it. If it is odd, I can't do it, right? But I know that the number of odd degree vertices is even, right? So there are 6 vertices here. So I have a cycle of cost on the 6 vertices of cost no more than optimum, right? I can break up the cycle into 2 perfect matchings on that set. Yeah? So either the matching given by these wavy edges or the other edges has to have cost no more than half the cost of the cycle, right? Yes? So there is a matching on this odd degree vertices of cost no more than opt over 2. Is that clear? Right? For any subset of even size, there is a cost of the perfect cost, it doesn't matter what the set is, there could be any subset. As long as it's of even size, there is a matching of cost no more than opt over 2. Why? Because you look at the cycle which is the optimum cycle on them, and you can break up the cycle into 2 matches, right? Because it's an even length cycle. One of them has to have cost no more than opt over 2, right? Because together their cost is the cost of the cycle. Yeah? Questions? Yeah? So that's it. That's the proof, right? That what is the algorithm is very simple, right? The algorithm is you compute a spanning tree, minimum spanning tree. That's efficient, right? You can do it easily. We all know how to do it. And then you look at the odd degree vertices and compute the minimum cost matching. Okay, but this is not so easy, right? We didn't cover this in class. Well, because it's a matching in a non-bipartite graph. and it has costs on it, right? And it's not an easy problem to solve. You can do it in polynomial time, but it's a little bit more tricky. We've seen how to solve minimum cost matching in bipartite graphs. Okay, but this graph is not bipartite because it's a complete graph on this entire set of vertices with with distances, right? So finding a minimum cost perfect matching is a little bit more complicated. We didn't do it in this class, but we saw only bipartite graphs because we can reduce it to flow, but you can solve this problem also efficiently. Okay? So if you believe that, then the algorithm is very simple and the analysis is also not very hard. Okay? Okay, the cost of the tree is at most opt, the cost of the matching is at most opt over 2, so 3 opt out. Okay? You know, this was done in 1976. Okay? And we have not been able to improve it in 2016. 40 years, right? Okay? So big, TSP is the most fundamental discrete optimization problem. We have not been able to improve this ratio in 40 years. Okay? It's remarkable that it has withstood so many attempts, and you can teach it, right, as we taught it in you can even teach it even lower 374 if you want, right? It is such a simple algorithm, right? And in 76, but we haven't been able to improve this approximation algorithm. Okay? It is the most famous open problem in approximation algorithms. And so some other results I want to mention. There's a very famous result due to Sanjeev Arora and Joe Mitchell in 1996 that if your points are in the plane, for example, and you want to find a TSP, you can get arbitrarily close to the optimum solution. You can get 1 plus epsilon approximation for any fixed epsilon in polynomial time. Okay, it was a big breakthrough. Many results followed from that, and you can change the dimension to 3 dimensions, 4 dimensions, as long as the dimension is fixed and n is growing, you can still do it. The dependence on d will grow exponentially too, right? Okay, fixed dimension you can do. There are many generalizations, right? So that's an important result. And in practice, metric TSP, geometric TSP instances are fairly well solved because of this huge effort. There's something called the Concord TSP solver by these famous authors, Applegate, Bixby, Kautal and Cook. They have a book, they have code. You can, if you Google it, you'll find it easily. It solves metric TSP and geometric TSP instances of size, hundreds of thousands to optimality. So even though it's an NP-hard problem, many instances can be solved near optimally or optimally by using mathematical programming techniques, LP solvers with branch and bound, huge number of tricks, right? It's again, a huge effort. If you're interested in the history of TSP and both the theoretical and practical aspects, they have nice books, both sort of technical books, and also recently Bill Cook has written a more easily accessible general audience book as well, right? So if you're interested in TSP, you can solve that. Okay? Okay. So that's about TSP in undirected graphs. I want to briefly mention directed graphs, right? So directed graphs are always a little harder, right? Because they don't have symmetry, and some cases they are easier. Undirected graphs can be harder, but most of the time. Well, what is the notion of, is there a notion of metric TSP in directed graphs? Because if you don't have that assumption, it's impossible to approximate it. So again, let's think of it in the following way, right? I give you a directed graph. Think about, Champagne with one-way streets, right? Okay? Or not too many one-way streets, but if you go to New York City, there are clearly going to be many one-way streets, right? Okay, but what do we want? Say, I want to visit some number of things in New York City, right? But I have one-way streets, right? So that's the directed graph, right? But I want to start at some location, and I want to visit some number of locations, right? It's again okay to visit a vertex more than once, right? I want to visit everybody and come back to the starting point, but I don't care if you visit a city more than once, okay? So what does it mean really, right? One way of thinking about it is I make the graph a complete directed graph now. That means that every pair has this way and this way. But I don't, because it's a directed graph, the length of the path from u to v, length of the edge from u to v can be different from the length of the edge from v to u. Okay? I might have a very, to go, so it might be that, you know, to go from here to here I have an edge, but to come back I have to go somewhere else, right? Okay? But what I do have is still the triangle inequality in the directed sense, right? It's the following thing. What does it mean? If I want to go from location U to location W, it cannot be more expensive than going from U to V and V to W. Even in the directed sense, right? You know, because I can't go to W by going from U to V and V to W, right? So that's called a symmetric triangle inequality, right? So here is an example, right? You know, so this is here is a graph, right? You know, and here is a tour, which is what I'm looking for really, right? You know, I start with the graph. See, look at this, right? It goes like this, and then it goes like this and comes back. Okay? So it is visiting this vertex more than once, right? That's okay. Okay, that's what we're looking for. That's called ATSP or asymmetric TSP, which is the equivalent of the metric TSP. That you're allowed to visit a vertex more than once, but you have to come back. The graph is directed. Okay, right? Okay, this is a harder problem, right? Somehow it is a harder problem if you think about it a little bit. Another way of thinking about it, just like in the old problem for undirected, you want to find a connected Eulerian subgraph. Okay, but here Eulerian means in the directed sense. That means the in degree must be equal to out degree, as opposed to degree must be even, which is different in undirected. Okay, you want to find a connected graph such that the in degree is equal to out degree. Okay, some history. In 1980, people came up with a very simple log n approximation algorithm. That's what I'm going to show to you without doing too much of the analysis in pictures. It's not very hard. And nobody improved this till 2010. Okay, maybe the constant was improved, you know, by a little bit. You know, from 2 it became 1.9 or something, right? You know. And in 2010, there was a big breakthrough, okay? They improved it to from log n to log n or log n. You say, oh, wait a second, why are you so excited, right? Because the method was very powerful, okay? It is based on linear programming, and the method was very exciting, very powerful, led to a lot of beautiful ideas. And then, in 2015, there was another big result, where the result was improved from log n or log n to log n to some big constant. Again, you know, in practice it's completely useless, right? You know, but this was even more interesting result, right? You know, this required a heavy duty machinery. Okay, the math involved relied on. It's not even easy for me to. I haven't read that paper because it's so difficult to read that paper, right? And it uses very beautiful, not just because it's difficult, right? You know, in math, difficulty also goes with not always, but with depth, right? You know, it's difficult not because people want to make it difficult, but it is really hard, right? You know, it's a very powerful result, and people believe that there is a constant factor approximation for this problem, right? But we are not there yet. And there's a very nice conjecture which would imply that, and that's very easy to explain to people. It's just using spanning trees of a graph. But even that will take some time to understand what it is, but the conjecture is very simple and pretty. So all these results are trying to prove that conjecture, and they have proved partial results, and that's where we stand, right? Okay. So that's, you know, TSP inspires a lot of powerful techniques. That's why it's interesting, right? Okay, so let me just quickly tell you how they got this log n approximation, and it uses some of the ideas that we've already seen. It's very simple, right? Okay, instead of that, I'll show you a picture, okay? Okay, okay, what is a cycle cover? You've seen it in homework, right? I give you a directed graph. What is a cycle cover? It's a collection of cycles that partitions the vertex set. Remember that? Okay, and we saw how to find out whether a directed graph has a cycle cover. How did you do it? Do you remember? Don't remember. If I give you a graph and say, is there a cycle cover? That means what does a cycle cover look like? Like this, right? A collection of directed cycles which together cover all disjoint cycles, right? Do you remember how we reduced it to what? To bipartite matching, right? Yeah? When is a graph have a cycle cover? A cycle cover means that one edge in and one edge out, right? If I give you a guarantee that every vertex has exactly one edge in and one edge out, then it must be a cycle cover. Yeah? To check whether how to find that, you say, okay, create 2 copies of each vertex. Yeah? And put an edge between one left copy to the right copy. If UV is an edge, you put an edge from left copy to the right copy, and then check whether the graph has a perfect matching. Okay, it's a homework problem, you may remember, right? That will tell you whether the graph has a cycle cover, right? So we have reduced finding the cycle cover problem, finding a cycle cover, to finding a perfect matching in a bipartite graph. Okay. You can also solve the minimum cost cycle cover by using minimum cost flow, right? Minimum cost perfect matching. Okay? Okay, you can solve that, right? Using just the same reduction. So the algorithm is very simple. It says find a cycle cover, minimum cost cycle cover. What is the cost of a cycle cover? Is the sum of all the costs of the edges. We can do it by reducing it to minimum cost to matching. Okay? So why is this good? Well, what is the cost of a minimum cost cycle cover? What can you say? Is it going to be more than optimum or less than optimum? Why is it going to be less than equal to optimum? Because the optimum itself is a big cycle, right? Yeah? Optimum is a cycle, while we are not connecting everything. We are giving you many disjoint connected component like cycles, right? So our cost cannot go up, right? I am giving you something which is weaker. Yeah, remember optimum is a cycle, right? Yeah? So this should be only cheaper than the optimum, no? And we can find it efficiently. That's a nice thing, right? I can't find a single cycle, but if you allow me to use as many cycles as you want, I can find it efficiently by using bipartite matching. Okay? So I find this. So what am I going to do now? It's not connected, right? I have to connect it. So I said, okay, if I find a one cycle, I'm great, I'm done, I find the optimum solution, right? So I won't do it. That's okay. So what I do is, I'm still not connected, so I pick an arbitrary vertex from each cycle, okay? And I say, okay, now find another cycle cover, but only restricted to these 4 vertices. In the graph, restricted to those only 4 vertices, okay? Okay, then I might find these 2 cycles, right? Okay, and then say, okay, this still not connected, so I'll take one vertex from each of these cycles, a pink guy here, a pink guy there, and I find a cycle cover in that graph. Well, if I have only 2 vertices, then it will find it, right? It will just one edge here, that's the only cycle cover there is, right? Okay, now what do? I take these edges, and these edges, and put them all together. What do I get? I get an Eulerian graph, right? Why? At each step I have a collection of cycles, right? So in degree is equal to out degree, right? Okay. So at every step I have an Eulerian graph and I am putting more and more of them, right? Okay. So I get an Eulerian graph, right? And it's connected, right? Why is it connected? Because if it is not connected, I kept on adding more and more, right? Yeah. So once I get this graph, I can do an Eulerian tour of this graph and visit everybody. And how much will I pay? I'll pay the total cost of all these edges, no more than that, right? Yeah. Okay. Now the only question is, how much is the total cost of all these edges? What do you think? Well, we already argued that the black edges are no more than optimum, right? What about these orange edges? or can there be total cost of the orange edges, I claim, is also no more than optimum. Why? Because if you look at this blue vertices, there is a tour on the blue vertices of cost no more than opt, just like in the previous case, right? I take a subset of the vertices. If there is a tour in a big set, there must be a tour on this blue vertices because I can shortcut, right? Because I have this asymmetric property is still, if I have a big tour on all the vertices, then there is a tour on the subset of the vertices of cost no more than the big tour, no? Yeah? So again, by the same argument, I claim that the cost of the orange edges is no more than optimum. Yeah? Same reason, the cost of this whatever cycle on the pink vertices is no more than optimum. Right? So together, how much am I paying basically? The total 3 times the optimum here, right? But in general, how much will I pay? It depends on how many iterations I do, right? Okay, what's the worst case number of iterations I will do? In the worst case is n, right? I claim no, I'll actually do only log n. Why? Because in each step, I reduce the number of vertices by half, right? Why? Because a cycle, remember the cycle cover I can't have isolated vertices in a cycle cover. So each cycle is of length at least 2, right? So the number of vertices that the number of blue vertices is no more than half of the original number of vertices. Okay? And the number of pink vertices is no more than half of the blue vertices. And if I keep going, so at each step, the number of vertices I have goes down by half at least. So I don't do more than log n iterations. Yeah? So the total cost I pay is log n times opt. Right? And that's it. That's it. That's a simple algorithm, right? Again, we are trying to find an Eulerian subgraph of the original graph of not too much more cost. So what is the ingredient we used? The ingredient we used is cycle cover, right? And how did we solve cycle cover? Because we knew how to solve bipartite matching. How did we solve bipartite matching? Because we knew how to solve flow, right? So it's important to know all these tools, not because they are arbitrary, but you build, right? Once you have these concepts, you need to know some tools to be able to develop new algorithms, right? So that's the algorithm at the end is very simple, and that's it, right? I won't do the analysis because it's not hard. What I did is just, right? If you want to understand it more formally, you can look at the notes. Yeah. And that's it. That's the log n approximation for the asymmetric case, and these things are well beyond the scope of this class. I don't even teach this in the graduate level approximation algorithms class because it takes too much time, right? They are more advanced, right? But they're very interesting, right? Sophisticated tools. So that's it. That's the algorithm, and that's the more or less the analysis. You can look at the notes if you want to. Right. So one thing I want to mention is that the approximation algorithms we did, other than the vertex cover approximation using LP, were all simple combinatorial algorithms, right? That we just did something greedy or something like this. Most of the algorithms were combinatorial using existing algorithms in a simple way. Most of the advanced stuff needs more sophisticated techniques relying on linear programming or convex programming techniques. I didn't do, in fact you can do all this with LPs also, I didn't do it because it requires more machinery and more time, okay? But most of the algorithms are not based on simple combinatorial algorithms. You need more advanced machinery, right? So if you take another advanced class, you'll see it. Okay, that's all I wanted to say. Next lecture is, there is no lecture, next lecture is mostly a review. I'll come and answer questions. So I'm going to leave the room and give you the evaluation forms. Can I get somebody, a volunteer, to take the forms back to the academic office? Can one of you do that for me? You just have to collect the forms and put them in the things and dump it in the give it to the academic. Okay, can do that. Okay, let me, you know the drill? Do I need to tell you the process? I hope not, right? Okay, there are two forms because there are two instructors, right? You know, I was discussing with somebody else yesterday. Apparently, right, it's not uncommon that there will be two instructors, right? And there will be, I mean, it's natural sometimes that the evaluation for the two instructors is different, but they also evaluate the course differently, right? So, you know, if they like the instructor, they give higher ratings for the course as well, which is kind of, you know, a little odd, right? The course is a package, right? So try to be consistent on that front at least, right? You know, it's kind of our biases are okay. Let me okay. So the form should say have the names, right? So I'll put the. I can turn this off.